let's talk about something you probably haven't thought about since, I don't know, grade school: rounding numbers. It seems so basic, right? But what if I told you there's a hidden story of fairness and unfairness buried inside that simple rule? Yeah, the way we round numbers has this deep history and some, well, surprisingly serious consequences. So let's get into it. Okay, so I'm going to start with a question that, seems almost too easy. What is 7.5 rounded to the nearest integer? You know the answer to this one. It's 8. Of course it's 8, right? I mean, that's what they drilled into our heads in school. If it ends in a 5, you round up. Simple as that. Case closed. Or is it?
But here's the thing. What if that rule, that always round up rule, isn't actually fair when you apply it over and over again? What if there's a tiny hidden flaw in there that, believe it or not, can cause some pretty big problems? So to really get why this matters, we have to rewind a bit, because this idea of connecting math and justice, it's not some new thing. Nope, we're talking thousands of years old.
Yeah, let's go way, way back. Think ancient Mesopotamia. For the very first states to even work, to be seen as legitimate by their people, they had to rely on math. I mean, think about it. Taxes, divvying up grain, dividing land, all of that had to follow precise mathematical rules. For them, this idea of a just measure wasn't just some catchy phrase. It was literally the foundation of their entire society, of justice, of power. Okay, so let's jump back to today. It's time to put that old school rule under the microscope and see what's really going on. So the official name for this rule we all learned is round half up. And that's exactly what it is. It's a tiebreaker. But it's a tiebreaker that says any number ending in 0.5, well, it only gets pushed in one direction. Always up.
And that is the problem. For just one number, it seems totally harmless. But when you start applying this rule to a huge set of data, you get this persistent upward bias. Just think it through for a second. Numbers ending in 0.1, 0.2, 0.3, and 0.4, they all get rounded down. That's 4 options. But numbers ending in 0.5, 0.6, 0.7, 0.8, and 0.9, they get rounded up. That's 5 options. That little 0.5 is always going in one direction, and it slowly, systematically pushes the average of all your data just a little bit higher than it's supposed to be.
And this is where you can really see it. Look at the left side with our good old school rule. Every single number ending in 0.5, 2.5, 3.5, 4.5, they're all marching in one direction, up, up, up. But now look at the column on the right. This is a different method, and you can see the decisions are balanced. Sometimes it rounds down, sometimes it rounds up. It's like this slide just revealed the invisible thumb on the scale that's been there the whole time in the method we all just took for granted. So you might be thinking, okay, this is a cool little math puzzle, but it's not just some nerdy debate. This tiny upward bias, it can have really big, measurable consequences out in the real world. Take this, for example. A study looking at student grades in Brazil found something pretty shocking. When they used that biased round half up rule on student scores, it actually created real, significant gaps in the final grades between different racial groups. And that's the key takeaway here. A math procedure that seems totally neutral on the surface can actually make existing inequalities worse, or even create new ones. And this chart just makes that so incredibly clear. It takes that abstract number from the study, 0.94, and makes it totally concrete. You can literally see the gap, the difference that a simple rounding rule can create. Wow. It's just a powerful reminder that the little mathematical tools we choose to use, they have real stakes.
Okay, so if the rule we all grew up with is flawed, then what's the answer? What's the alternative? How do we actually find a fairer way to round these numbers?
Well, let's meet the solution. It's called round half to even, but you might also hear it called banker's rounding or statistician's rounding. And this is the method the pros use when accuracy over huge amounts of data is absolutely critical. The rule itself is actually pretty elegant. When a number is a perfect tie, exactly halfway, you don't just automatically round up. Instead, you round it to the nearest even number. So how does that actually work? It's pretty simple when you break it down. If you have a tie, that 0.5 at the end, you just look at the digit you're rounding to. If that digit is odd, like the 1 in 8.015, you round up to make it even, so it becomes 8.02. But if it's already even, like the 4 in 8.045, you round down to keep it even, making it 8.04. So 2.5 rounds down to 2, but 3.5 rounds up to 4. See? It elegantly solves the entire bias problem.
And why is this so much fairer?
Well, it's because over the long haul, it all balances out perfectly. About half the time you're rounding up on those ties, and about half the time you're rounding down. It completely cancels out any systemic bias. In fact, this method is so good, so robust, that it's the default rounding method in the IEEE 754 standard. That's the standard that basically tells most of our computers and calculators how to do their math.
But this story doesn't end there. What if you need to be even more precise? What if your goal is to eliminate every single last drop of potential bias? Well, that's when the search for perfect mathematical justice gets even cooler.
This brings us to something called stochastic rounding. And the idea here is it's so beautifully simple. When you have a number that's exactly halfway, you basically flip a coin. There's a 50% chance it gets rounded up and a 50% chance it gets rounded down. By using pure probability, it guarantees perfect long-term unbiasedness. Kind of neat, right? All right, so we've gone from ancient Mesopotamia all the way to modern supercomputers. What's the big takeaway here? What does this all mean? I think it's this. The rules of math aren't like the laws of physics that we just discover out in the universe. They're tools. They're things that we, as people, design to solve problems. They're human inventions. And as our own understanding of big ideas like fairness and bias gets better, well, the tools we design get better too. We refine them to build fairer, more just systems. And that kind of leaves us with one last big question to chew on. If a rule as simple, as basic, as innocent-looking as rounding can have a hidden bias with real consequences, what other neutral rules in our lives, what other systems or algorithms that we interact with every day might be worth a closer look?